Welcome back, everybody. Let's get started in section 6.5. There are quite a few things going on in this section, so I'm going to break it up into a couple of videos. This first video will look at simplifying nth roots, and then rationalizing denominators. Then we'll move on to the next video with the rest of the operations we need to deal with. This first key concept is exactly what we were doing in the last section. Basically, all it's saying is that if we have a product under a radical sign, we can split that product up into two separate radicals. Likewise, if we have two separate radicals, we can put those two radicals together as a product under a single radical sign. It's all this expression right here means. And the book gives us a couple of simple examples here. If we have the square root of 2 times the square root of 8, we can actually multiply those and put them under a single radical, in this case, a square root radical. So 2 times 8 is 16, and we end up with the square root of 16. In this case, it's looking only for the principal square root, so 4 is our answer. In the second example, we have the cube root of 3 times the cube root of 9. As long as these indices are the same, we can combine the 3 and 9 under a single cube root sign. So we multiply the 3 and 9 and put it under a single cube root to get the cube root of 27. And we know there's only one root in this case, and it happens to be 3. Well, that seems easy enough, but let's try a couple of examples here with some variables. The square root of 32x to the 8th power. So what the product property tells us is that we can split this product into two pieces. Now, in simplifying this, all we need to do is deal with each factor separately. So we can simplify the square root of 32. Well, let's see. 32 is 16 times 2. That means we've got a perfect square in there, 16, and we can pull 4 outside the radical. In the variable expression, we're also looking for a perfect square hiding in the radical sign. And indeed we have one, x to the 4th squared. That should be x to the 8th, since whenever we raise a power to another power, we multiply those exponents. So we've just simplified x to the 8th into x to the 4th squared. What's nice about this is that since we have a perfect square inside the yellow radical here, we can pull x to the 4th out in front. When we do so, all that's left inside is 1. Now it's just a matter of multiplying these two expressions. We have 4 times x to the 4th outside the radical, and inside we've got 2 times 1, which is easily expressed as just 2. So the product property here allowed us to separate the radicand, the part underneath the radical sign, into two pieces, and then to deal with each of those separately as we simplify. To formalize things a little bit here, let's define what we mean by simplifying nth roots. All we're trying to do in this case is arrange the radical expression so that this is true. The expression should contain no factors that are nth powers of any integer or any polynomial. And you can see that's exactly what we did in example 1 here. We made sure that we didn't have any perfect squares in both the coefficient portion and the variable portion. We took all of those out of the radical, and that left us with just the square root of 2 inside the radical. That's the only thing that if we tried to take its square root, we wouldn't end up with either an integer or just some variable raised to a power. That's our entire mission in simplifying nth roots. And this product property gives us the power to pull apart radical expressions or put them together in order to simplify them. And just as there's a product property, there's also a quotient property. It works exactly the same way. If we have the nth root of some fraction, a over b in this case, we can split that up into two radicals that are still a fraction. And vice versa. As a pretty simple example, let's say we have the square root of 27 divided by the square root of 3. Well, this quotient rule tells us that we can combine those two radicals into a single radical containing a fraction. Now it's pretty easy to simplify the radicand, the part under the radical, since 27 divided by 3 is just 9. And since we're just looking for the principal square root here, our answer ends up being 3. So the quotient rule allowed us to take these two radicals, one in the numerator, the other in the denominator of a fraction, and put them all under one radical sign, and then simplify. Just as a quick example with variables, let's say we were trying to take the cube root of the fraction x to the 6th over 8. Well, it would be a lot easier if we could deal with this as two separate cube roots, since we know the cube root of 8 is 2. So let's use the quotient rule and split this apart. Now we can look at this in two parts. In the numerator, x to the 6th is just x squared cubed. So it turns out we do have a perfect cube there. Let's write that out. So since we have this perfect cube hiding under the cube root sign, we can pull it out in front. And that leaves us with just x squared on top. And as we said, the cube root of 8, obviously 2, so that ends up on the bottom here. The other thing we're interested in doing in this part of the section is dealing with rationalizing the denominator. I know you've heard of this before. It's just a general custom in algebra that we don't want to have radicals in the denominator of a fraction. So in the past, we've talked about how to deal with square roots in the denominators of fractions. Today we want to talk about how we're going to deal with nth roots there. It's a slightly different process. But if you'll recall, in the case where we do have a radical on the bottom of a fraction, if it's a square root, getting rid of it is as simple as multiplying by 1. But we want to multiply by 1 in a very special way. We want to multiply by 1 in the form of the radical divided by the radical. This way we're not changing our original fraction, we're just making it look different. When we do this multiplication, on top we get 2 times the square root of 3, and on the bottom we get the square root of 3 times the square root of 3. Well, lucky for us, that's just 3. So, even though this expression doesn't look a great deal simpler than the original expression, we have managed to get that radical out of the denominator. Now we have a rational number in the denominator, which is why we call this rationalizing the denominator. This is pretty easy. It gets a little bit more complex, as we see in the table above, when we have an nth root instead of a square root. Instead of just multiplying by the square root again, in this case, if we have some nth root in the bottom of a fraction, we need to multiply by this quantity. It seems a bit strange. Let's look at the example they provide. In this case, the culprit is the cube root of 2, which is on the bottom of the fraction. They're telling us that we want to multiply again by 1, but 1 in a very special form. We're going to take the cube root of 2 squared divided by the cube root of 2 squared. And it's important that we see how this fits the pattern of the nth root of b raised to the n minus x power. All it's asking us to do is look at the denominator in this way. Here's our n, it's a 3. Underneath we have some expression b, and it's raised to a power. In this case, it's just raised to the first power. So in order to get rid of this radical expression, we need to multiply by, again, a cube root, and our base stays the same here, 2. But in this case, we want to take n minus the power that we had on our base originally. This is n, here is the power we had originally. So we're going to raise this to the 3 minus 1 power. So when we actually do this multiplication, what we end up with on the top is 5 times the cube root of 2 squared. Well, 2 squared is 4, so we can simplify that right away. But the cube root of 4 is not an integer, so this is as easy as we're going to get on this one. In the denominator, however, using the product rule, we can combine the radicands of these two radicals into one cube root. Now, remember, when we multiply two things that have the same base, but different exponents, we add the exponents. So in this case, we're going to get the cube root of 2 to the third power. Of course, the top stays exactly like it was. But in this case, these 3's canceled. We have a perfect cube inside the cube root. So what we end up with is just the numerator divided by 2. Again, this might not look a lot simpler than the original expression, but we've managed to get that cube root out of the bottom of the fraction, therefore rationalizing the denominator. I'm going to move on to a couple new topics in the next video, and then we'll come back and look at more examples of this to help it make sense. Thank you, everybody.